A nuclear aircraft carrier is not designed around an airplane. It is designed around interfaces, steel thickness, pipe diameters, power margins, cooling loops, data trunks, deck coatings, and human survivability limits. Once those interfaces are welded into place, they become fixed constraints. Everything that operates on that deck must obey them. That is the starting point for understanding why the USS Gerald R. Ford cannot simply adopt any aircraft that appears operationally convenient. The public debate often frames the issue as a choice between simplicity and complexity. The F-35B Lightning II lands vertically. It does not require catapults. It does not require arresting wires. From a surface perspective, this removes mechanical stress and reduces launch system dependency. The Royal Navy operates the HMS Queen Elizabeth without catapults or arresting gear. The U.S. Marine Corps operates F-35Bs from amphibious assault ships. The configuration works within those system boundaries, but a supercarrier is not an amphibious assault ship scaled up. It is a different industrial object. A 100,000-ton nuclear carrier is optimized for sustained sortie generation, deep strike radius, and high deck throughput over extended deployments. The internal architecture, magazines, fuel storage, elevators, deck cycle geometry, assumes a certain class of aircraft performance envelope. The Ford class was not built as a neutral platform waiting for any aircraft. It was built around expectations of catapult-launched, arrested recovery, fixed-wing aviation. This is where the concept of a frozen baseline becomes decisive. When the keel of a ship like the Ford is laid, structural decisions are locked in. 10-inch steel plates are welded. Bulkheads become load-bearing realities. Cooling pipes are routed through compartments that will later be sealed behind armor and insulation. Electrical generation margins are allocated. You cannot revise those fundamentals without cutting steel. And cutting steel on a nuclear carrier is not modification, it is surgery. In 2005, when the Ford's design baseline was locked, the F-35C Lightning II was still in development. Its final weight distribution, exhaust characteristics, data requirements, and integration profiles were not fully mature. Interface control documents were evolving. Yet the ship had to move forward. The United States Navy chose concurrency, building the hull while the aircraft and launch systems were still being finalized. This is not unusual in complex defense programs. It compresses timelines, but it transfers technical risk downstream. The result is what engineers describe as a synchronization gap. The ship was delivered according to the specifications available at the time of design lock. The aircraft matured according to its own development timeline. When both systems reached operational reality, their assumptions no longer perfectly matched. This is not a failure of intent. It is the consequence of industrial sequencing in multi-decade programs. Understanding this gap requires shifting perspective. The Ford is not rejecting an aircraft out of preference. It is operating within thermal tolerances, structural fatigue limits, electromagnetic compatibility margins, and bandwidth ceilings defined years earlier. Every carrier deck is a thermodynamic environment. Every catapult stroke is a structural event. Every aircraft launch is an acoustic hazard zone. These are measurable thresholds, not political variables. The question, therefore, is not whether one aircraft appears simpler. The question is whether the fixed geometry and material science of a nuclear supercarrier align with the physical and digital demands of a given platform. Once steel is welded, geometry becomes destiny. The rest of this analysis will examine how that destiny collided with the evolving characteristics of the F-35 family, beginning with the variant that seems, at first glance, to solve everything. At first glance, the F-35B Lightning II appears to eliminate the most controversial components of a supercarrier. No electromagnetic catapults, no arresting wires, no complex launch sequencing. The aircraft can take off in a short roll and land vertically. From a purely mechanical perspective, that seems to remove stress from the ship. But aircraft design is a zero-sum equation governed by volume and weight. The F-35B achieves vertical landing by installing a lift fan directly behind the cockpit. That fan is not an add-on. It is a structural commitment. It consumes internal space that would otherwise be allocated to fuel tanks or weapon bays. In engineering terms, it is a permanent mass penalty that only functions during vertical operations. During cruise flight, it becomes inert weight. On a small carrier or amphibious assault ship, this trade-off is rational. The platform lacks catapults. It cannot launch heavier aircraft with large wings and extended range. The lift fan enables fixed-wing aviation where it otherwise would not exist. The Royal Navy structured the HMS Queen Elizabeth around this compromise. Their operational focus emphasizes regional power projection and integration with Allied infrastructure. Within that doctrine, accepting reduced internal fuel volume in exchange for operational flexibility is logical. A nuclear supercarrier operates under different constraints. The USS Gerald R. Ford is designed to remain at sea for extended periods, operating far from shore-based support. Its strike packages are planned around reach. When internal fuel is reduced, combat radius contracts. The F-35B's approximate 450 nautical mile combat radius reflects the geometric consequence of its lift fan architecture. The F-35C, by deleting that fan and reallocating internal volume to fuel, extends that radius beyond 600 nautical miles. A difference of roughly 150 nautical miles is not marginal in a contested maritime environment. Carrier positioning is determined by threat envelopes, anti-ship cruise missiles, anti-ship ballistic missiles, and land-based air defense systems. If the air wing cannot project power beyond those envelopes, the carrier must move closer. Moving closer shifts the carrier from a standoff asset into the adversary's effective engagement zone. The aircraft's geometry directly influences fleet survivability. There is also the question of payload configuration. The lift fan reduces internal bay flexibility. Carrying heavier 2,000-pound class munitions internally becomes more constrained. When internal space is insufficient, external carriage becomes necessary, which increases radar cross-section and reduces stealth. On a supercarrier intended to operate in high-threat environments, stealth and range are not optional attributes. They are structural requirements of the doctrine. Replacing catapult systems with vertical operations would not simplify the Ford's mission profile. It would fundamentally redefine it. The ship's nuclear reactors provide sustained electrical output and endurance specifically to support high-tempo, fixed-wing operations with heavy aircraft. Using that energy infrastructure to operate shorter-range vertical fighters would underutilize the platform's design intent. The mismatch would not reduce complexity. It would reduce capability relative to the ship's scale. The comparison to amphibious lightning carriers, such as the USS Tripoli, further illustrates this point. When an amphibious ship embarks F-35Bs, it temporarily shifts its role from troop transport to limited sea-based air power. That flexibility is valuable, but those ships were not built for sustained, high-intensity blue water strike cycles. Their magazines, deck layouts, and aviation fuel storage do not match supercarrier throughput. The apparent simplicity of the F-35B is therefore contextual. It simplifies operations for ships without catapult infrastructure. It does not optimize performance for a nuclear supercarrier designed to project air power across oceanic distances. The lift fan solves one engineering constraint while creating another. On a platform built around reach, that second constraint becomes decisive. This leads to the central architectural choice. If vertical flexibility is not aligned with the Ford's mission geometry, then the carrier variant, built without the lift fan and optimized for fuel and wing area, must carry the burden. That aircraft is the F-35C, and integrating it introduces a different class of system friction. The F-35C Lightning II exists because distance governs naval warfare. Removing the lift fan was not a cosmetic adjustment. It allowed engineers to reclaim internal volume for fuel, and to enlarge the wing area for lower approach speeds and greater lift efficiency. The result is a carrier aircraft with a combat radius exceeding 600 nautical miles and structural adaptations for catapult launch and arrested recovery. This configuration is not about convenience. It is about operating beyond the effective range of shore-based threats while maintaining meaningful strike capacity. For a carrier strike group, range translates directly into survivability. A difference of roughly 150 nautical miles alters where a carrier can stand relative to anti-ship ballistic missile envelopes and long-range coastal air defenses. If the air wing cannot reach targets from outside those envelopes, the carrier must close the distance. Closing distance compresses reaction time and increases exposure. The geometry of fuel storage inside the aircraft therefore becomes a fleet-level variable. The F-35C also changes how the air wing functions as a network. It is not designed to replace legacy strike fighters like the F/A-18 E/F Super Hornet. It is designed to reshape their employment. In a contested air defense environment, non-stealth aircraft carrying external stores are more detectable. Radar cross-sections increase as weapons are mounted externally. In such conditions, survivability declines before weapons release range is reached. The F-35C addresses this by penetrating first. Its low observable profile allows it to operate inside dense radar coverage long enough to gather targeting data and distribute it across the strike package. The aircraft's sensor fusion architecture consolidates radar, electro-optical, and electronic surveillance inputs into a coherent battlespace picture. That data is transmitted to accompanying aircraft and command nodes. In practical terms, the F-35C functions as a forward sensor and targeting coordinator, while other platforms carry larger external payloads. This arrangement modifies sortie logic. The Super Hornet becomes a weapons truck positioned outside the densest threat rings. Long-range standoff munitions can be launched based on targeting information refined by the stealth aircraft. Without a forward node capable of surviving initial detection cycles, the rest of the formation operates with degraded awareness. The air wing shifts from parallel strike elements to a layered architecture in which one platform absorbs detection risk in exchange for information dominance. From the carrier's perspective, this changes deck cycle planning. Aircraft launch sequences must consider fuel states, sensor roles, and mission data synchronization. The F-35C's larger wingspan and folding mechanism alter spotting density on the flight deck. Elevator scheduling and hangar placement adjust accordingly. The aircraft's footprint influences how many sorties can be generated per hour. Carrier aviation is a throughput problem. Each aircraft type modifies that throughput differently. The strategic logic is consistent. Extend reach, penetrate first, distribute data, and allow heavier payload carriers to operate from relative safety. This doctrine aligns with blue water operations in contested regions. It does not eliminate risk, but it redistributes it across a layered force structure. However, designing an aircraft optimized for range and stealth does not guarantee seamless compatibility with the ship that must launch and recover it. The Ford class was locked into structural and systems assumptions years before the F-35C's final characteristics stabilized. When the finished aircraft met the finished ship, mismatches emerged. Not in philosophy, but in physics. The next layer of analysis examines how a 2005 ship design encountered a 21st century aircraft whose thermal, structural, and digital demands exceeded earlier projections. When the design baseline for the USS Gerald R. Ford was frozen in 2005, the ship entered a phase where geometry, load paths, and utility routing became fixed realities. At that moment, the F-35C Lightning II had not yet completed flight testing. Critical performance parameters, final weight growth, exhaust temperature behavior, power draw characteristics, and maintenance footprint were still evolving. The ship and the aircraft were progressing on partially independent timelines. This overlap is known in defense acquisition as concurrency. Instead of waiting for the aircraft to mature completely, the Navy advanced ship construction to preserve industrial capacity and avoid delaying fleet recapitalization. Concurrency compresses schedules, but it converts uncertainty into retrofit risk. Once hull construction advances beyond certain milestones, changes are no longer design edits. They become structural interventions. The Ford-class internal architecture was optimized around projected interface control documents available at the time. Cooling capacity for jet blast deflectors, electrical distribution for launch systems, network backbone bandwidth, and deck structural reinforcement were sized according to best estimates. Those estimates were not arbitrary. They reflected the data available during the early 2000s. However, as the F-35C matured, its operational characteristics crystallized differently than early projections. Weight growth in developmental aircraft programs is common. Additional systems, reinforcement, and survivability features accumulate mass. When that mass interacts with carrier landing dynamics, specifically arrested recovery at high descent rates, the structural load transferred into the deck and supporting hull increases. Carrier landings are not gentle glides. They are controlled impacts, designed for consistency rather than softness. The structural frequency and magnitude of those impacts must align with deck reinforcement assumptions locked years earlier. Simultaneously, the aircraft's propulsion system matured into a configuration that concentrated thrust and exhaust heat into a single, high-energy nozzle. The thermal flux interacting with jet blast deflectors and deck coatings exceeded some early predictive models. Materials selected under 2005 constraints now faced a propulsion system optimized later in the development cycle. This was not a conceptual error. It was a timing differential between ship steel and aircraft refinement. Digital infrastructure followed a similar pattern. The F-35C's mission systems require significant data throughput for mission planning files, threat libraries, and encryption updates. In 2005, shipboard network capacity planning reflected then-current aviation data loads. Over the next decade, airborne sensor fusion and digital mission systems expanded in scale. The aircraft became a high-bandwidth node in a distributed battlespace network. The ship, already structurally committed, had to adapt. These mismatches formed what can be described as a synchronization gap. The Ford was delivered structurally complete, but not fully aligned with the final operational demands of its intended primary aircraft. Addressing that gap requires planned incremental availabilities, periods in which the ship returns to the yard not for cosmetic updates, but for invasive modification. Bulkheads are opened, cooling lines are rerouted, electrical systems are augmented, deck surfaces are re-engineered. From a systems perspective, this is not evidence of institutional neglect. It is the downstream effect of aligning two highly complex platforms that matured on overlapping but not identical schedules. Large warships operate on multi-decade life cycles. Aircraft development cycles compress differently. When these cycles intersect, physical friction emerges. The critical question is not whether friction occurred. The question is how that friction manifests, structurally, thermally, digitally, and what engineering pathways exist to reconcile it without undermining the carrier's core mission. The next layer of examination moves from procurement timelines to the physical realities of flight deck operations, where geometry and material limits become immediately visible. A carrier flight deck functions less like a runway and more like an industrial conveyor system. Every movement, taxi, spotting, launch, recovery, elevator transfer, must occur within tight spatial and temporal margins. Throughput is the governing variable. The introduction of the F-35C Lightning II alters that throughput because its geometry and operating profile differ from previous generations. The F-35C has larger wings than legacy strike fighters. They fold, but even folded, the aircraft occupies a distinct footprint. That footprint influences how many aircraft can be staged on deck before a launch cycle. Spotting plans that worked for the F/A-18E/F Super Hornet require recalibration. Elevators must move aircraft between hangar and flight deck with different spacing tolerances. Minor differences in wingspan propagate into measurable differences in sortie rhythm. Landing dynamics introduce a second layer of stress. Carrier recovery doctrine emphasizes consistency. Pilots maintain a controlled descent rate and intercept the arresting wire without the extended flare common in land-based operations. The impact energy is absorbed by arresting gear and transmitted into deck structure. If aircraft weight or distribution changes, the frequency and amplitude of stress cycles also change. Deck reinforcement assumptions locked years earlier must now accommodate updated landing profiles. Beyond structural loading, deck choreography becomes more complex when aircraft require larger maintenance footprints between sorties. The F-35C's low observable coatings and sensor systems demand specific inspection and servicing protocols. Maintenance crews require access zones that influence parking density. Each additional constraint reduces flexibility in how aircraft are arranged during rapid cycle operations. Hangar deck operations mirror this complexity. Aircraft moved below deck must align with fire suppression systems, power hookups, and maintenance bays sized for projected dimensions. Even slight deviations in actual aircraft envelope affect clearance margins. Over a 50-year service life, these margins compound into operational constraints. The deck is also a thermal environment. Jet exhaust impingement zones define safe positioning during engine run-ups. With propulsion characteristics concentrated through a single, high-thrust nozzle, exhaust patterns differ from twin-engine aircraft. Aircraft positioning relative to jet blast deflectors must account for that concentration. Deck crew exposure zones adjust accordingly. Movement pathways are redrawn, not for convenience, but for survivability and material endurance. Sortie generation, often measured in launches per day, depends on minimizing congestion while maintaining safety. Increasing aircraft capability can unintentionally decrease deck efficiency if geometry and procedures are not synchronized. This is not a binary failure. It is a throughput recalibration problem. The carrier air wing is a system of systems. Each new platform changes the flow dynamics. These physical adjustments, however, represent only part of the integration challenge. The more subtle constraint lies beneath the deck, inside server rooms, cable trunks, and network nodes. The F-35C is not simply an aircraft requiring fuel and weapons. It is a high-volume data consumer and distributor. And when a 21st-century data architecture meets a 2005 network backbone, friction emerges that steel alone cannot resolve. The F-35C Lightning II is often described as a stealth fighter, but operationally, it functions as a data node embedded in a combat aircraft. Before engines start, it requires mission data files, threat libraries, navigation updates, and encrypted communication keys. These data packages are not trivial in size. They are measured in gigabytes and, over time, terabytes of cumulative storage and processing. That requirement shifts part of the integration burden from steel to bandwidth. When the USS Gerald R Ford design was locked in 2005, shipboard digital infrastructure reflected the expected aviation data demands of that period. Carrier networks were robust by contemporary standards, but they were not built around aircraft acting as distributed sensor fusion servers. As the F-35 program matured, onboard processing expanded, sensor resolution increased, and mission planning complexity grew. The aircraft's digital appetite exceeded earlier planning margins. On a carrier, bandwidth is not infinite. Fiber trunks must route through armored compartments. Server rooms require cooling capacity and electrical redundancy. Cybersecurity measures introduce additional processing overhead. Expanding these systems after hull completion involves reopening compartments, rerouting cables, and upgrading power distribution units. These are invasive procedures performed during planned incremental availabilities, not routine pier-side maintenance. The issue is not simply download speed, it is synchronization timing. Aircraft preparing for launch must ingest mission data without delaying deck cycles. If data transfer windows extend beyond planned preparation time, sortie rhythm degrades. Carrier aviation depends on predictable sequencing. Data latency becomes an operational variable. The F-35C also transmits information once airborne, Sensor fusion allows it to generate refined targeting data that can be distributed to other aircraft, surface ships, and command nodes. This requires secure, high-capacity links that integrate with shipboard combat systems. Compatibility is governed by evolving standards. When aircraft software updates introduce new communication protocols, ship systems must adapt. Unlike land bases, carriers cannot rely on fixed infrastructure upgrades. They must carry the architecture at sea. This digital burden compounds with physical integration. Increased server capacity raises cooling demand. Cooling demand increases electrical load. Electrical load draws from finite reactor-generated margins allocated during initial design. While nuclear carriers provide substantial power reserves, distribution pathways and transformer capacities were dimensioned years earlier. Expanding network capability therefore becomes a coordinated upgrade across multiple subsystems. From a systems perspective, this represents a shift in what aircraft integration means. Historically, integration focused on structural compatibility and launch mechanics. With the F-35C, integration extends into information architecture. The aircraft does not simply operate from the ship. It depends on the ship as part of its computational ecosystem. This creates a layered synchronization challenge. Steel and structure must align with landing loads. Thermal systems must absorb propulsion heat. Network backbones must sustain digital throughput. Each layer operates on different engineering timelines, but they converge on the same deck. Physical friction was visible first in thermal stress and deck wear. Digital friction followed more quietly inside equipment rooms. Both stem from the same root, aligning a mature, physically committed warship with an aircraft whose capabilities expanded during development. The next constraint emerges where propulsion energy meets material science, on the flight deck itself, under concentrated exhaust temperatures that test the limits of steel and surface coatings. From a thermodynamic standpoint, the F-35C Lightning II introduces a propulsion profile that differs materially from earlier carrier aircraft. The Pratt & Whitney F135 engine concentrates approximately 43,000 pounds of thrust through a single exhaust nozzle. When afterburner is engaged, exhaust temperatures can approach levels that challenge conventional deck protection systems. The issue is not whether steel melts. It is whether repeated thermal shock degrades structural integrity over time. Jet blast deflectors, JBDs, represent the first line of thermal defense during catapult launches. When an aircraft throttles up prior to launch, exhaust is directed into these panels. Earlier deflector designs assumed distributed exhaust patterns from twin-engine aircraft such as the F/A-18E/F Super Hornet. Concentrated exhaust from a single high-energy nozzle changes heat distribution. Passive steel panels without active cooling risk accelerated deformation. The response was not to simply increase plate thickness. Additional mass introduces structural penalties and complicates actuation mechanisms. Instead, engineers redesigned deflectors to incorporate active cooling loops using copper-nickel (CuNi) alloys. Seawater is circulated through internal channels to absorb thermal energy before it transfers into structural members. This transforms the deflector from a static barrier into a heat exchange system integrated with the ship's fluid infrastructure. Deck surface coatings presented a parallel challenge. Traditional epoxy-based non-skid coatings were adequate for decades of carrier operations. Under higher thermal flux, however, these coatings can experience spalling. Rapid heating causes differential expansion between coating and substrate, leading to flaking. Detached fragments become foreign object debris, FOD, posing ingestion risks to high-performance engines. Even small particles entering the intake of a modern turbofan can cause costly damage. The mitigation strategy involves shifting from adhesive surface treatments to mechanically bonded metallic ceramic overlays applied through twin-wire arc spray techniques. In this process, aluminum or specialized alloy wires are electrically melted and atomized onto the deck surface at high velocity. Upon impact, particles flatten and bond mechanically at a microscopic level. The resulting surface tolerates higher thermal cycling without catastrophic delamination. These modifications illustrate a broader systems principle. Thermal integration is not isolated to the deck. Cooling seawater diverted to deflectors affects pump loads and corrosion management. Additional plumbing occupies space and requires maintenance access. Protective coatings influence traction characteristics for deck crews operating in high-wind maritime conditions. Every solution propagates secondary adjustments. Importantly, these thermal adaptations do not imply design negligence. They reflect updated empirical data gathered during aircraft testing. When real exhaust measurements exceed predictive models, material responses must adjust. Carriers operate on decades-long timelines. Aircraft propulsion systems evolve more rapidly. Integration therefore becomes iterative. Thermal stress, however, is only one manifestation of energy transfer between aircraft and ship. The launch process introduces dynamic forces that interact with aircraft landing gear resonance. Solving that interaction required not structural reinforcement, but algorithmic refinement within the electromagnetic launch system. The transition from steam catapults to the electromagnetic aircraft launch system was not pursued simply to increase launch power. It was pursued to increase control authority over the launch profile. Steam catapults operate through pressurized pistons, delivering force in a relatively fixed impulse curve. That curve is effective for aircraft within established weight classes, but it lacks fine-grained modulation. Emails, by contrast, uses linear induction motors capable of shaping acceleration digitally. When the F-35C Lightning II began test launches, pilots reported a vertical oscillation in the nose during the first moments of acceleration. This phenomenon, often referred to as bobble, was not random vibration. It was resonance. The force curve of the electromagnetic shuttle interacted with the natural frequency of the aircraft's nose landing gear strut. When external force input aligns with structural resonance frequency, oscillation amplitude increases rapidly. In a carrier launch, those first seconds are critical. Pilot visual stability and sensor alignment matter. Redesigning the landing gear would have required extensive structural requalification, additional testing, and production delays. Instead, engineers leveraged the programmable nature of EMALS by modifying the initial acceleration profile, softening force application during the first milliseconds. They shifted the frequency interaction away from the resonant peak. The oscillation dampened without altering aircraft hardware. A mechanical interaction was resolved through software adjustment. This solution highlights a core trade-off. Steam systems are mechanically simpler and historically reliable. They have decades of operational data. However, they cannot tailor launch energy to each aircraft with precision. Emails introduces greater complexity, including power conversion modules and control algorithms that initially experienced reliability challenges. Early operational testing revealed higher than desired failure rates compared to mature steam systems. Yet, emails provides flexibility that steam cannot. Launch force can be calibrated for heavier strike fighters or reduced for lighter, structurally sensitive aircraft. This capability becomes significant as carrier air wings incorporate unmanned systems. Future carrier-based drones may have lower structural tolerance to abrupt acceleration. Steam's binary power profile would impose design penalties on such aircraft. Emails, though less mature in reliability, offers a scalable force envelope. For the USS Gerald R. Ford, this represents an investment in controllability over historical dependability. Reliability metrics continue to improve through incremental hardware refinements and software updates. However, the trade-off remains visible. Greater system sophistication introduces new maintenance demands and troubleshooting complexity. Power electronics, cooling systems, and control software require specialized technical oversight. The resonance episode illustrates a broader systems principle. Integration problems are not always solved by adding material or redesigning hardware. In digitally mediated systems, force can be reshaped algorithmically. That capability is itself dependent on sufficient electrical generation and computational infrastructure, both integrated into the Ford-class architecture from inception. Launch dynamics, however, are not purely structural or digital phenomena. They intersect with human survivability. Propulsion energy does not only stress steel and landing gear, it produces acoustic environments that approach biological limits. Addressing that constraint required adaptation, not of the ship, but of the personnel operating on its deck. Propulsion energy manifests not only as heat and thrust, but as acoustic pressure. The F-35C Lightning II, operating at high power settings, generates sound levels that can approach or exceed 150 decibels at close proximity. At that intensity, sound is no longer perceived simply as noise. It becomes mechanical stress, transmitted through air and bone. Flight deck crews operate within meters of aircraft during launch preparation and recovery cycles. Even with traditional double hearing protection, earplugs and earmuffs, extreme acoustic energy can propagate through bone conduction pathways. Prolonged or repeated exposure risks permanent hearing damage. In this environment, personnel survivability becomes a systems variable, not an individual precaution. Earlier carrier operations already required hearing protection, but propulsion advancements increased acoustic intensity and frequency range. The concentration of thrust in a single high-output engine changes the acoustic signature, compared to distributed twin-engine configurations like the F/A-18E/F Super Hornet. The spectral distribution of sound energy affects how protective systems must perform. To address this, upgraded flight deck helmets, such as the HGU-99/P, integrate active noise reduction technology. Microprocessors embedded in the helmet distinguish between harmful high-frequency engine noise and lower-frequency human speech. Instead of blocking all sound indiscriminately, the system filters selectively. Crew members can communicate while reducing exposure to damaging acoustic energy. This is not a comfort feature. It is an operational necessity to maintain coordination in high-noise zones. However, active noise reduction introduces its own dependencies. Power sources must be reliable. Electronics must withstand salt spray, vibration, and impact. Maintenance cycles expand. When protective equipment becomes electronically mediated, failure modes shift from simple wear to component malfunction. Human survivability becomes tied to microelectronics supply chains and maintenance discipline. Acoustic mitigation also influences deck procedures. Personnel positioning relative to exhaust plumes is adjusted. Launch sequencing considers cumulative exposure time. Training incorporates stricter enforcement of protective protocols. The cost is not measured only in equipment procurement, but in procedural rigidity. This illustrates a recurring theme in integrating high-performance aircraft onto carriers. Each increase in capability, thrust, heat, digital processing, propagates new constraints across ship systems and human factors. None of these adaptations occur in isolation. Cooling loops, launch algorithms, deck coatings, and protective gear all represent responses to concentrated energy density. At this stage, the question becomes structural rather than technical. Why accept these cascading adaptations? Why retrofit cooling systems, upgrade network infrastructure, refine catapult algorithms, and re-engineer deck surfaces instead of retaining legacy aircraft or adopting a simpler vertical landing model? The answer lies not in aesthetics or prestige, but in operational geometry. Specifically, the interaction between range, survivability, and the contested maritime environment. The decision to absorb these integration costs is anchored in operational distance. A carrier does not project power simply by existing at sea. It must position itself relative to threat envelopes. Anti-ship ballistic missiles, long-range cruise missiles, and layered air defense systems create expanding engagement zones extending hundreds of nautical miles from shore. If a carrier's air wing cannot strike from outside those zones, the carrier itself becomes part of the target set. The difference between a 450 nautical mile and a 600-plus nautical mile combat radius is not abstract. That additional reach allows the USS Gerald R. to remain farther from hostile coastal systems while still delivering precision strike capability. In a contested theater, those extra miles translate into reaction time, maneuver margin, and survivability probability. Fuel volume inside the F-35C Lightning II directly influences fleet positioning options. Retaining only the FA-18EF Super Hornet would simplify integration. The Super Hornet is mature, well understood, and compatible with legacy deck systems. However, it is not optimized for penetrating dense, integrated air defense networks. When carrying external stores, radar cross-section increases. Detection ranges expand. In high-threat environments, survivability declines before weapon release distances are achieved. The F-35C alters that equation by combining range with reduced observability and sensor fusion. It is not intended to replace the Super Hornet entirely, but to enable it. In a strike package, the F-35C operates forward, collecting and refining targeting data within contested zones. That data is transmitted to supporting aircraft positioned at safer distances. The strike group becomes layered: stealth forward, massed ordnance rearward. This arrangement also intersects with launch technology. The electromagnetic launch system is not optimized solely for the F-35C's mass. It is designed to accommodate a spectrum of future aircraft, including lighter unmanned platforms. Steam catapults deliver force through a comparatively fixed impulse. Emails allows force modulation tailored to airframe tolerance. As naval aviation shifts toward mixed manned-unmanned air wings, that controllability becomes structurally important. The trade-off remains visible. EMALS has required iterative reliability improvements. Network infrastructure upgrades demand shipyard time. Thermal retrofits consume budget and labor. Yet the alternative, retaining legacy launch systems and shorter-range aircraft, would constrain adaptation to evolving threat environments. The Navy has chosen to accept short-term integration friction to preserve long-term operational flexibility. This decision does not eliminate risk. It redistributes it across time. Early ships in a new class absorb retrofit burdens so that follow-on hulls incorporate adjustments from inception. As subsequent Ford-class carriers enter service, many thermal, digital, and launch refinements are integrated at construction rather than retrofit stages. The broader systems pattern is consistent. A nuclear supercarrier is not valuable because it is large. It is valuable because it sustains high-tempo, long-range, survivable air operations without reliance on host nation basing. The F-35C extends that capability envelope under modern threat conditions. Integration difficulties represent the friction of aligning industrial timelines with evolving aerospace performance. What remains unresolved is how quickly reliability improvements and digital upgrades can converge with operational demand, and how future unmanned systems will further reshape deck geometry, bandwidth allocation, and launch sequencing. Those variables will determine whether the current synchronization gap narrows permanently or re-emerges in new forms as technology continues to advance.